Hi. I thought I'd give you a few tips on converting from base 10 to base 2 and a few related notes to that issue here. Let me start by looking at the powers of 2. You should be familiar with the first 10 powers of 2 at least, starting with, on the right, 2 to the 0th, first, second, third, all the way up to 2 to the 10th, which is 1024. Knowing that 2 to the 10th is approximately 1,000 comes in handy in doing some estimations. For example, 2 to the 35th is 2 to the 5th times 2 to the 10th cubed. And since 2 to the 10th is approximately 1,000, we can estimate this number to be 32 times 10 cubed, all cubed. Or 32 times 10 to the 9th, 32 billion. Going back to this list of powers, I'm putting them in opposite order because these are the numbers, the powers of 2 that correspond to the binary digits, and the rightmost digit, or bit, in the case of binary notation, is the units corresponding to 1, and next going to the left is 2, then 4, and so on. Let's look at a few examples. Let's start with 29. Okay, the trick for small numbers is very simply to, if you're aware of the powers of 2, pick out the power of 2 that, the largest power of 2 that fits into, in this case, 29, which would be 16. 32 is a little bit too large. So you take 16 and you subtract 16 from 29, that leaves you 13, and you do the same thing with 13. 13 contains an 8, subtract 8 away, that leaves 5, 5 contains a 4, take 4 away, that leaves 1. And now notice that there's no 2, we can't fit 2 in, but we use the extra 1, and the binary digits, this sum, 16 plus 8 plus 4 plus 1, corresponds to the binary representation 11101, indicating that there's 116, 18, 14, 02s, and 11. Of course, the place values are determined starting from right to left by the 1s, 2s, 4s, and so on. So for really small numbers, under 100, you should be able to convert from base 10 to base 2 this way. Let me show you the algorithm that's used, or described in the book, that uses successive pairings. And I'm going to use a small number because it would be kind of tedious to describe the algorithm with a larger number, but this really comes in handy when you have a very large number. So here's a bunch of things. I want to count them and describe the number of these things in base 2. So the idea behind binary is you group first by 2's. So I'm going to group a bunch of these things. I'm going to pair them up. Okay, so I've got 1 pair, 2 pairs, 3, 4, 5. But I'm not going to count them. I'm not going to count the pairs. I'm just going to group them. Okay, when I've done that, when I've grouped all the pairs, notice I have one lonely item left. That 1 means that the base 2, or binary representation of the number of these things, has a 1 at the end. The 1's bit is 1. Now, however many pairs I have here, I pair them up into 4's. Okay, so that's why I kind of did this in a certain way. The reason I already had them paired up, paired the pairs a little bit, was to make this faster. Notice by pairing up the pairs, I have a bunch of 4's, but I do have 1 pair left over. So that 2 indicates that there's a 1 for this number of things in the 2's position, 2's bit. Repeat this again. Well, I've got pair up the 4's. Pair up the 4's into 8's. And again, I have 1 left over. So there'll be a 1 in the 4's bit. Okay. Next thing I do is I pair up the 8's. I'm not going to move these around. It's obvious here that I have 2 8's. Pair those up. There's into 116. No 8's left over, so there'll be a 0 in the 8's bit, and a 1, a single 16, 1 in the 16's bit. So what we have is, starting from the highest power, I had a 116, 0 8's, 1 4, 1 2, and 1 1. So this number of things is represented in base 2 by this number right here, but that's equal to, we represent, if we want to get a feel for what this is in base 10, it's 16 plus 4 plus 2 plus 1. And see, that's 23. So there are 23 of these things. And notice that I didn't count them. I didn't count how many there were when I identified the binary representation. I did it by successive pairings. This next thing is some Mathematica code that you don't have to really follow, although if you're interested, this would be a way to program how to find the list of binary digits, binary bits of a number. With 1460, it happens pretty quickly, and even with a large number like this that I have here, which I believe is something like 5 to the 50th, I picked up a very large number, it doesn't take any time at all to use the repeated pairings of the number, dividing by 2. And you can do this for just by doing this by hand also. I won't do the whole thing, but if I have a number like 431, I would divide by 2. My remainder is going to be 1 since it's an odd number, and I'm left with, when I divide by 2, 215. And I now divide by 2 into 215 and keep repeating this, and the remainders are what represents the binary bits. One more quick thing. I'm going to just show you how in Mathematica there are built-in functions for this, so you don't have to do this for large numbers or program it even. Here's the function called integer digits for 100 factorial. Now, 100 factorial is this number. The integer digits function very simply creates a list of these digits that you see here. But if you add a second argument to the function, so integer digits 100 factorial, comma 2, you get the binary numbers. There's another function called from digits, which if you have a list of digits, you can get back the number. Now, if I take the bits 11101, which going back here, that's 29, that was what we had for 29, and I use from digits with that, I get 11,101 because, again, the default is taking the digits and we're converting to a base 10 number. But if you do provide a 2 here, you get the number 29. So that goes back. If you start with a number, compute the integer digits base 2, and then from digits base 2, you're back where you started. One final Mathematica function, the base form function, base form 29.2 displays 29 in its base 2 representation. Frankly, that's not as useful because you can't compute with that. It's just a formatting, but can come in handy sometimes, I suppose. One final thing, I want to show you how this is done in Sage. Although Sage doesn't have quite the same range of functions. In Sage, the function bin of 29, will give you a string. Now, the 0b indicates binary, and then notice the 11101 is the same output as we had before. This is a little bit more compact output than with Mathematica. And factorial 100 factorial, bin of that. Very quickly you get the same. It's the same sequence. 0 after what follows 0b the bit is the base 2 representation of 100 factorial. There's also a couple other functions, oct, which in Sage converts a number to base, the integer to base 8. Base 8, this is 29, is 3 times 8 plus 5. That's what we know is 24 plus 5. And the hex, base 16, hex of 29 is 1d. That's base 16, so 29 is 16 plus 13, 116, and d is the digit for 16, for 13, sorry. Okay, so hope this helps you in studying base 2 conversion.